Good morning, ladies and gentlemen. Okay, so we've already done a bit of reading on this, and you've had a chance to use some of the labs to practice some of the skills of using the measurement units and tools in science. Here's just a quick video to introduce you to some of the core concepts, vocab terms that you might want to have some notes on to study for a quiz. So here we go. First of all, when we talk about scientific units, what we're referring to is the SI, or Système International. It's French for just the international system of units, meaning a set of units all the scientists kind of agreed upon that were defined in order to allow us to measure and differentiate all the different concepts in the universe. So we have a unit for all the lengths, so linear, one-dimensional distance, mass, kilogram in kilograms, time in seconds, and temperature in Kelvin. Now you might think Celsius, we'll come back to that later, but those are the four that are really going to become relevant for this class. Things like electrical current in amperes and candelas for brightness or luminous intensity, moles for substance, those are important units, but they will not really come up in this class. So the main four you really want to be familiar with are length, mass, time, and temperature as meters, kilograms, seconds, and Kelvin. All right, we'll look at those more as we go. So with length, there's one-dimensional length, which we would simply measure in meters. Meters is abbreviated with the lowercase letter m. If you then take meters and multiply a length times a height or a width, you then get a two-dimensional unit, meters squared. The little 2 in the corner can kind of remind you that you're now talking about a two-dimensional shape instead of a one-dimensional line. But if you want a volume, a three-dimensional space that something occupies, then you're talking about length times width times height. Remember, the definition of volume is a three-dimensional space that an object occupies in our world, whereas length is just one side of that object or one dimension of that object. We have volume of fluids, which can then be measured with a slightly different unit. So if we're talking about liquids or gases, you often see 2-liter bottles. So liters are our scientific unit for measuring liquids. A liter can be symbolized with the letter L, but the difference here is that this is already three-dimensional. You don't have to worry about like liters squared or liters cubed. It's just liters, and that's three-dimensional all by itself. So we can make a direct comparison between liters and meters or centimeters because 1 milliliter is defined as exactly 1 cubic centimeter. Or you can scale that up and say that if you're talking about 1 liter or kind of half of a 2-liter bottle, that would be equal to 1,000 cubic centimeters. So both of these two units, the volume calculated as length times width times height, or the volume measured in liters, these are actually the same concept, and you can convert one to the other directly. Okay, getting now into mass and its comparison to weight. Here on Earth, generally, we don't really notice a major difference between mass and weight as often because gravity pulling on mass causes weight. And since we're always being pulled by gravity here on Earth, there's really never a time that you're not experiencing weight. So we can use a scale to figure out how much weight an object has and therefore how much mass it has. But mass is actually the property of the matter itself. So no matter where you are in the universe, whether there's gravity or not, it doesn't matter. An object will still have the same amount of matter. However, if you change where an object is in the universe, then it will alter how heavy the object feels because you are altering how much gravity is actually pulling on the object. So you physically have the same 50 kilograms of mass, whether you're standing on Earth or Mars, but you might weigh a different amount on Mars than you would on Earth because Mars itself doesn't pull on you quite as hard. Similarly, floating in outer space, if you try to punch a bowling ball, you're going to break your hand the same way that you would trying to punch a bowling ball here on Earth, because whether or not you can push that bowling ball forward has nothing to do with its weight and everything to do with its mass. Okay. Time. Time is actually very simple because the unit of measurement for time does not change from your normal units to scientific units. Scientists will still use the same seconds, minutes, hours, days, etc., going up in larger units over for measuring large amounts of time. However, when we start dealing with smaller units of time, then you start getting into those SI prefixes. I'll come back to those more later, but things like centi, milli, micro, nano, you may have heard of, say, milliseconds to describe thousandths of a second. So 1,000 milliseconds equal to 1 second is a way that a scientist could measure something like an explosion or some very fast chemical reaction like the inflation of an airbag that takes 70 milliseconds or 70 thousandths of a second. And we need that chemical reaction to be that fast. So we need a very short unit of time to describe that. Temperature. Temperature is measured in Kelvin as the SI unit. However, you might mistakenly think that Celsius would be that common unit. It's because Celsius was invented for metric about 200 years ago, and it's been replaced since then. So Celsius is still the more popular unit worldwide, and it was used by scientists up until about 50 years ago. But the reason they changed it is because if temperature is the measurement of the average speed of the particles, then the slower the particles move, the smaller the number should be. But logically, the slowest anything can move is 0, not moving at all. Even going backwards is moving. So there is no such thing as negative movement. Scientists then decided that it didn't make sense to have a system like Celsius, where 0 is the freezing point of water, because then anything colder than ice would have a negative number, and that doesn't make sense. Even in Fahrenheit, our American unit for temperature, they had this issue where there was a 0 that didn't mean the coldest something could ever be, and there were still negative numbers in Fahrenheit that didn't make sense. So they decided to measure the very coldest an object could ever be when the particles are standing perfectly still. They called that absolute 0, and they created a whole new measurement system called Kelvin that represents the absolute 0, no negative numbers, but each unit step, each notch on the thermometer is actually the same size as a Celsius degree. They just moved where 0 is located. All right, density. Density is the idea when we want to compare how tightly packed matter is. So it's calculated as mass divided by the volume, so that if you're talking about, say, a box full of feathers, it could have the mass of all the feathers, but spread out over a large area because each feather is very lightweight, but takes up a lot of room. So a huge box full of feathers won't necessarily contain as much mass as, say, a smaller brick, because that brick has the matter more tightly packed. So if you're looking at the classic brain teaser or trick, what has more mass, a ton of bricks or a ton of feathers? The reason for the trick is because we automatically think about density as if density is the same thing as total mass, and it's not. If you have 1,000 bricks, we're saying you have exactly 1,000 bricks, but 1,000 bricks would be relatively small compared to 1,000 feathers, which would be very, very large. So if you're thinking not just about the mass, but how big it is, then the density could be very different. So to put this into this example, 1,000 bricks could be maybe only 1 cubic meter, about the size of a desk, while 1,000 kilograms of feathers, a ton of feathers, might be the size of, say, a whole room. And so to describe the difference in density, we do 1,000 divided by 1, mass divided by volume, so 1,000 kilogram mass divided by 1 meter volume, to say that bricks might have a density of 1,000 kilograms per meter cubed, while feathers would have a mass of 1,000 kilograms, but also a volume of 1,000 meters cubed. And that much larger volume means 1,000 divided by 1,000, it only has a density of 1 kilogram for every 1 meter cubed. So 1,000 to 1 or 1 to 1 the feathers have a much smaller density. All right, final thing for this video, when we are describing any unit of measurement, so it doesn't matter if this unit is liter, meter, gram, second, you name it, we can then add prefixes to it. So when we talk about prefixes, the words we're using are things like kilo and centi and milli, popular ones like that, or less popular ones like nano and pico and femto, or giga, tera, mega. So anytime you're talking about in computers, a megabyte or a gigabyte or a terabyte, you're actually describing orders of magnitude, multiples of thousands or tens, to describe how many zeros you would add to the quantity of that unit. For example, if I have 1 meter, then it's just unit 1 meter. But if I add the prefix kilo, I'm multiplying it by a factor of 1,000. So K in front of the M, km, kilometers, kilometer, would be 1,000 of the original base unit of meter. Similarly, if I were talking about centimeters, I would then be adding this C prefix, centi, to say it's 1/100th of the base unit. So a centimeter is 1/100th, 100 times smaller than a meter. All right, we'll leave the video here for this one. Have a wonderful day.